Okay, step number 3 is select the level of significance of what you're trying to test. Or, in stating it another way, what is the amount of alpha error that you are willing to accept? So what is the probability that you will commit an alpha error, or in other words, reject the null hypothesis when in fact the null hypothesis is true. So you reject it in error and accept the alternative hypothesis. Then step number 4 is to determine the critical value of the test statistic. And the primary factor is, again, like it was in all of the other instances, in making this choice is the direction of the hypothesis and the statistical test. So in other words, is it a one-tailed test or a two-tailed test? And given this particular instance, we're going to choose the Pearson's correlation with regard to the different types of correlations, because we have in our example weight and systolic blood pressure. So we will use the Pearson's correlation and a two-tailed test of hypothesis, because we don't know with absolute certainty whether after the changing of these particular medications, whether weight is going to change and whether the systolic blood pressure changes in concert with the weight. So step number 5 is to do the calculation. Now, 99.9% of the time you're going to use the computer. 99.99% of the time I use the computer. And when you have thousands of people who are involved in your study, the only way to do it without making sure that your hair grows white and your beard grows white and you get to see your children before they graduate from college is to use the computer. But we're going to give you an example of how you might do it, not for the purposes of doing it on a test, but to show you theoretically how the idea of a correlation works. We'll do both the conceptual and the computational formulas. So, first of all, you calculate the sum of the independent variable and the dependent variable. You calculate the product of the independent variable and the dependent variable for each individual. And you determine the t-score critical value to determine whether to reject or not the null hypothesis. Now, you say t-score. What are we doing t-scores for? Because we're doing correlation coefficients, or R's. Well, we'll get to that in just a minute. Because think about it in the same way as a mean score. You have to calculate a mean score and then get the variability or the confidence interval around the mean score. Well, in this instance, what we will be doing is calculating a correlation coefficient, or an R, and then we're going to have to get the 95% confidence interval around that correlation. And we'll have to calculate a t-value for us to accept or reject this in the critical value. Now, I'm certain, now that I think back on it, that I have absolutely forgotten to tell you to turn to page 194 in your text, that this particular example that we're going to use comes from the textbook, and then we're going to use another one a little bit later on that doesn't come from the textbook. All right, so let's start off with the conceptual formula, or the conceptual equation. And anybody who does these kinds of these calculations would never use this. It's only to help you understand it. Think about the calculation of the sums of squares. And think about what I said about having a linear relationship and this imaginary line. So what you look at is, since you look at the sum of the individual's score minus the average score for the x variable, and you add all of these up, and then you do the same thing for the y, which is the individual's score on the second variable y, minus the mean score in this instance here too. So what you're doing is taking the sum of the products of the variation between the x variable and its group score or mean score, and the difference between the individuals in y and the mean score there. You take the product of that, and later on we'll get to that's why they call it the Pearson product coefficient. So basically what you have done is exactly the same thing that you have done in calculating the sums of squares, divided by, in this instance then, the sum of the same x minus x bar only squared and the sum of y minus y bar squared. And this is even more directly associated to the sums of squares and the square root of that. So what you're doing is you're looking at the relationship between an individual score and the average score. If the correlation were perfect, that would mean that each individual score and the average score is exactly the same. In the conceptual formula, what we're looking at here is a certain amount of variability. What we're looking at is the variability between an individual score and the mean score for that particular group. And if the individual score and the mean score were exactly the same, that means that there would be no variability here. And if we had a difference between the y variable, if there were no difference between that and the average of the y group, there would be no variability here as well. So in this instance, what we're looking at is zero variability from the line that we saw in a perfect line. So that means then the relationship between x and y is 1 minus 0, or 1. Now, the first time I saw that, I said, gee willikers, if you have an x minus x bar and it's 0, and y minus y bar is equal to 0, well, and that's in the numerator, why isn't that the correlation is 0 instead of 1? Well, as I looked at that formula, one of the things that you have to look at is that's the sum of the x minus x bar times y minus y bar. So we're not looking at necessarily 0 times 0. What we're really looking at is the sum of this multiplied times this. It's the basic formula that you use in high school algebra. Remember, that's all the math I had. So this means is that you've got x times y minus the x bar times y minus y bar times x, and so forth. So if you do a bunch of other calculations, what you end up getting is the sum of each individual person's score on x times each individual person's score on y times the sum of all of the x's, all of the y's divided by n. And so that's why, if you have a perfect correlation, that it is not 0, but rather 1. Now, before you all get too panic-stricken, I want to tell you that you're not going to have to recreate this formula. You're not going to have to calculate this formula on an exam or any of the assignments. It's only there to give you the sense of why a perfect correlation is equal to 1, and why you have a maximum of 1 for the Pearson's correlation, and a minimum, so to speak, of minus 1. So the range goes from minus 1 to plus 1. Okay, so let's move onward and upward to the actual formula that's used for the calculations for Pearson's correlation. Now, in this instance, what we're looking at is the sum of the product of x and y divided by the square root of the number of people and the sums of squares of the independent variable and the sums of squares of the dependent variable. So in other words, what you're looking at is the standard error of the mean in an equivalent way of looking at it. So you've got the sum of these products divided by the standard, basically the standard error of the mean. And that's why they call it not only correlation, but they call it Pearson's product moment correlation. So you're looking at this product divided by the standard error of the mean. Now, I think I'm going to have to ask you to wait for a second while I bring up my example in Excel to show you how this will work. Okay, well, let's take a look at then the association between weight and blood pressure in this instance. We're not going to use the example that's in the book, although we are going to use the same process. This uses the formula that we found for the computational formula. In this instance, then, here we have the systolic blood pressure, the weight in kilograms, and so in order to calculate the correlation, what you do is you take the difference between an individual score. In this case, person number 1 has a score of 137 is this systolic blood pressure. The average for the entire group is 138.2. So you see this x minus x sub bar, we come up with this x, which is a minus 1.2. We do the same thing for the weight. and we look at this person's weight, which was 75, minus the average weight of the group, which was 77.6 kilograms. So the difference is minus 2.6 kilograms. The next thing that you do is you multiply the x times the y, and that moves us all the way over here for a second. And that gives us then the xy that we saw in the formula, the sum of xy divided by n times the standard error of the mean for the x and the y. Okay, so what we have here then is the xy for this particular person. So in summary then, the individual score minus the average, the individual score minus the average, and then you multiply minus 1.2 times a minus 2.6, and you get a positive 3.12. Now, in order to find out the standard deviation, you have to come up with the sum of x squared, which is the 283, and then you divide it by the square root of n, which is the square root of 10 here. So to come up with the s sub x, you take the square root of the 283.6 divided by the square root of 10, which then gives you a 5.32 for the s sub x. So the square root of 283 divided by 10 is the square root of 28.3, which is about 5.3. You do the same thing for the y squared. You sum all of these up. You get 22.6 divided by 10, which is 22.6. You take the square root of that, and it's just under 5, which is 4.75. Then what you do is you take the 188 and divide it by 10 times 5.32 and 4.57. So it's this r, or the correlation, is equal to the sum of xy divided by 10 times 5.32, 4.75, and we come up with a correlation of 0.75. A correlation of 0.75 is actually a pretty big correlation when you look at it in some areas of research, such as social sciences research. In other areas, when you begin to look at physiology or things like that, it's actually not that much. Okay, well, let's take a look at how we calculate the t-score. And this is found on page 194 of the textbook. And in this instance, what we get is that t is equal to the correlation times the square root of the number of people in the study minus 2 divided by the square root of 1 minus the correlation squared. So, in calculating this out, we come up with 2.10 divided by 0.66696. And what you do is you use the degrees of freedom of, this actually should be n minus 2 degrees of freedom. So this should be 8 degrees of freedom. So we have t with 8 degrees of freedom. And so if you go to your textbook in Appendix A, and it would be Appendix A3, a 0.05 with 8 degrees of freedom, the critical value then is 2.306. So in this instance, you ask yourself, is the obtained critical value of 3.16 greater than the critical value of 2.31? So the answer is yes. Therefore, you are able to reject the null hypothesis of no different and accept the alternative hypothesis that the correlation that you have found of 0.75 is statistically significantly different from a correlation of 0. Okay, so let's take down the sample from the Excel spreadsheet and look at the next thing, is to state and draw the conclusion. So let's wait for a second, not too long though. The actual conclusion is the Pearson's correlation between systolic blood pressure and weight in kilograms is plus 0.75. But wait, what are we missing? Are we done yet? what do we have to do next? So our conclusion is that the t-score of 3.15 is greater than the critical value of t of 2.31. So we reject the null hypothesis, and the inference is that systolic blood pressure and weight are associated, so that as weight increases, so does the systolic blood pressure. So for someone like me, this should be a good reason to forego that last Checkers burger and just have 2 instead of 3 with dinner each night. Okay, before we move on to the SPSS printouts and that sort of thing, let's look at some of the things that one has to keep in mind as they look at an article in the literature to see if the authors avoid some of the pitfalls that happen sometimes as people interpret the data. So here we have the first of 6 things that we want you to keep in. Whoa! Dr. Doug the Data Dude. Dr. Doug the Data Dude. Well, with Dr. Doug the Data Dude showing up, I'd suggest that you coffee, wake up a little bit, come back and get these things and keep them in mind, okay? All right. First of all, the degree of association is normally not directly in proportion to the magnitude of the coefficient. So what do we mean by that? Well, if the coefficient, the Pearson's coefficient, is 0.50, that does not mean that the association is 50%. There is not a relationship in that instance between the coefficient and the amount of the association. As we talk about regression a little bit later on, there is a way of finding out the degree to which the variable predicts the next value of y, but it's not done in association. Second, if 2 variables are highly correlated, it is tempting to think of them as causal, but they are not. So if you have a situation in which you have an association or a Pearson's correlation of 0.90, p is less than 0.001, while they are highly correlated for some reason, it does not mean that they are causal. It means that in some fashion they are associated. And when we get to regression in a little bit, I'm going to give you an example of this in which one of the reasons that we use 2 variables to reduce confounding so that we know that in fact it is not causal. And what we're going to be looking at is the relationship between storks and the number of babies born in a year. So again, I want to dissuade you of the notion to think that just because a variable is highly correlated, it is causal. It does not cause it. The strength of the association depends upon the nature of the measurement, and that is to say the level of measurement as well as the kinds of subjects. In association, there are a variety of different ways of measuring association besides the Pearson's R. And Pearson's R, as I said, is most well suited when the variables are both continuous and quantitative. But other types of association measures include a rank ordering correlation, the biserial correlations, the point biserial correlations, contingency coefficients, correlation ratios, and partial correlations, and multiple correlations. And each of those, the level of measurement has some impact on the choice of which of those correlations is to be selected. We're not going to require you to know each of those. But what we are going to require you to know is that if you're looking for an association and it's not quantitative or numerical, then there are other types of associations that should be used instead of Pearson's correlation. And as you read the literature, if somebody's looking at the correlation between males and whether people are depressed or not, there are other types of association measures that could be used. Third, when the association is not a straight line, that is to say, it might be curvilinear, it might be S-shaped, or other types of distribution. The correlation is usually underestimated, particularly if you would use something that is linear versus something which is non-parametric, like the Spearman's row or the point biserial and so forth. Fifth, the correlations are usually reduced with what they call restriction of range. In other words, if you have a measure that goes from 0 to 100, you're better able to measure the correlation than if you have a measure that goes from 0 to 2. You will have much less of an underestimate, and it is certainly much more accurate without less bias. And then finally, the correlation, like anything else, is subject to sampling variation. And as you know from our discussions about the central limits theorem and so forth, that the sample size then is associated with sampling variation. The larger the sample size, the less sampling variation that there is, and the smaller the confidence interval. Let me give you an example. Limits within which 80% of the sample values of a Pearson's correlation will fall when the true correlation is 0. So in other words, our clinical hypothesis is that there is a correlation of 0 or there is not a correlation of 0. So if you have a sample size of 5, the correlation would be between minus 0.69 to plus 0.69. In other words, 80% of the values will be between that, even though the true population correlation is 0. With 15 people in the sample size, the range goes from minus 0.35 to plus 0.35. And for example, if a sample size is 200, it goes from minus 0.09 to plus 0.09. So that's the range of the error. So we have to be sure that when we have a correlation and the magnitude is very low, we have to be sure that the sample size is of significant size in order to truly test the difference. All right, so let's move forward into scenario number